Hello everyone, in this recording we'll discuss interactivity for temporal data. Before getting into any code, I want to discuss a high-level conceptual point. There's a notion called Norman's gulfs. These were named after Don Norman, who is a very influential design thinker for all sorts of computer interfaces. What it refers to is there are two ways that making interactivity can be difficult. Imagine when a user is looking at a visualization, they have some mental state, the computer has a certain state too. The difficulties can be, on the one hand, when the user looks at the computer screen, it might not be obvious how to actually interact with it, right? You might have a fancy graph. They might not know what to click, what to hover, whether moving the mouse does anything, right? So there's some processing mentally that has to go on before you figure out how to even make a query. Right? And then once you do figure out how to make an interaction and you have made a query, the screen is going to change, and the visualization is going to update. And it might not be obvious to the user what exactly changed, right? Like, how do you interpret the result after you've interacted with the visualization? If either of these processes are too difficult, then it kind of makes the whole visualization impossible to use. You want to make it as easy as possible to define a query and also to interpret its output. Right. So it's an important conceptual point. Now, how do we actually start implementing smooth kind of queries for time series data? One really common approach is called the overview plus detail technique. This is the idea, is sometimes called overview first, then details on demand. The idea is you can make it really obvious to a user how to query if you first show a really big overview, and then when the user is interested in a particular part of the dataset, they can indicate it by maybe clicking on it, hovering over it, pointing towards it. And then when they've indicated interest in that one area of the visualization, you zoom in, or you provide a lot of additional information about just that subset. Right? So it's a way of kind of navigating different scales. So we've already seen a couple examples of this before, right? Any kind of tooltip is already an example of the overview plus detail principle. It's showing specific information about one hovered element in the dataset. So let's do this with the electricity example from last time. Right. So we can implement this using a Voronoi mouse hover. Remember how Voronoi mouse hover works. It's like you take the entire visualization and you partition it into small Voronoi neighborhoods. Every time you transition from one Voronoi neighborhood to another, you're going to update the tooltip. You're going to say, here is the closest point on my Voronoi neighborhood. So let's look at the result before we look at the code. This is here the same electricity thing, but now I have this time series, right? And as I move my mouse, it's highlighting the closest time series. I think something kind of cool when you do it this way is you can see at a certain start point, what is the range and kind of the trajectories that it can take, given that you have a certain demand at a particular time of day. Yeah. There's something a little bit subtle about this implementation, though, of the Voronoi mouse over, is how do you actually define the neighborhoods when you have a time series? Right? It's not like a scatter plot where you just draw little kind of neighborhood regions around each point. Here, you want it to change as I move along, but then you don't have these very discrete values. So what you actually do is, in the background, each of these lines is associated with many, many small points, right? And then as I'm moving along the series, I'm transitioning from the neighborhood for one point on the line to the next point on the line. That's how the label knows to move as I'm moving, even though it's the same series. Right? So this is actually many small points. So if you remember in the last lecture, we gave each series is an array, right? So the overall data set is an array of arrays. But to build the Voronoi, you need to flatten that array of arrays into one long array. The reason you need to flatten it is you are just turning it essentially into like a scatter plot, where you have the points along each of the series, and you just need to figure out, which series and which point on that series am I closest to. when you do your Delaunay neighborhood drawing. So let's look at the actual implementation now that you see this. Right, so flat data I'm referring to is that long array of arrays flattened into one array. That can be done very easily in JavaScript using the .flat method. So if you look at the full code, I convert that array of arrays using this. At this point, I can call the Delaunay on that array. I need to use these kind of lookup functions to figure out what are the pixel coordinates associated with each element in the array. And then every time there's a mouse move, I'm calling this update series function. Update series is the thing that's telling me, should I highlight it red and should I move my label? Right. So this is exactly that code. Right. IX, this is the index of the closest point. Imagine in the background there's a whole bunch of points along each of these time series. It's looking up the closest point for my mouse. Once I figured out that closest one, I'm going to shade it in depending on whether the date of the currently, or I'm going to go through all the paths and I'm going to look at each path. Is its date equal to the date of the closest point? If it is, I'm going to make it red. Otherwise, just gray. Same thing with the width. If the date of this path is equal to the date of the point that's closest to, then we're going to make it a really wide path. Otherwise, it's going to be a very narrow path. Right, so that color and width is all changed here. I've also moved the tooltip, right? So I'm just moving it to wherever my Delaunay neighborhood is. This little raise is just making it so that I'm not buried in the background, right? So you want the red to be the highest point. Okay, so that's one example of the overview plus detail principle. Let's do the same kind of overview plus detail, but for our Gantt chart from last time. So let's just look at the results. It's going to look something like this, right? Remember before we had the Gantt is showing the length of these events. When you press collapse, it collapses all the events into one long array, or sorry, one long series, and you can see the areas which are really dark have lots and lots of overlapping events. You can imagine this being really useful if you had many groups of events. So if you had all the events belonging to one category and then all the events belonging to another category, you could at first show them overviewed in this kind of representation. So maybe there's like one purple and maybe there's another one that's blue. That's like a different group of events. And then you could, if you're interested in one of them, you could press a button, or maybe you can click on one of the rectangles and it would expand all of the sub-events for that one group, but not the others, right? So it's a way of kind of zooming in and out of groups of events. So this is just a simpler example because I only have this one group. Okay, how do we actually do it? Right. The main idea, to find a variable called collapsed. It's just saying, am I in my zoomed in or zoomed out approach? Right? It's just a Boolean, true or false. And then when I click on the button, I just toggle the value of this Boolean. If it's true, I set it false. If it's false, I set it true. And then I change the state by using these two functions. There's a function that's uncollapsing it, kind of like accordion, and another function that's collapsing them. Let's just look at the collapse function. The uncollapsed function is almost the exact same, just in reverse. Okay, this is the entire collapse function. What does it do? It looks at every rectangle in the Gantt chart, and then it just sets the y attribute to 0. Right? So y is 0 is the very top of the plot. Right? So that's what this first part is doing, and the transition is what makes it very smooth. And then what is this? This is just moving the axis, right? So the rectangles are 8 pixels high. So I moved it to the location 0, 8. So 0 is x, and all the way to the left. 8 means I want it just below this rectangle. It takes exactly the same amount of time so that they look like they're moving in sync with one another. Okay, And that's it. Here's another example, overview plus detail. This is called, this is a linked brushing example, right? So if I pull this brush over the entire series, it looks, they're just the same plot. But then if I'm interested in a particular time region, I can zoom the brush in, right? And now I can move my brush and look at the subtle trends within any particular area that I've selected using my brush. Right. This example is actually very similar to the scatterplot zoom example that we had before. Right. What's going on is whenever I move this brush, I am adjusting the domain of the scale used for this plot. Right. So I'm making the minimum value on the scale and the maximum value on the scale mirror whatever my current brush minimum and maximum are. And then once I've updated the scale, I just redraw the plot with the new scale. It's just like the scatterplot one, but in 1D. Okay, so those were all different kind of overview plus detail examples. Here's a slightly different idea. It's you can link plots, right? So we've seen linked brushing before, especially in Shiny. We had a lot of linked brushing examples. But you can do the same thing in D3, and it's often useful for temporal data. Right? So here's the bike demand data set. We've actually seen this example in a previous note. But this is just highlighting it's useful for time series, right? So as I go over temperature and humidity on the scatter plot, it's showing me these are all the associated series. Okay, so I think there's something where like if you are in this side of the plot, you tend to have a little bit lower bike demand in general. And then this side tends to have a little bit higher bike demand in general. And that's just it because when it's a warmer day, people are more likely to bike. The x-axis, I think, is the temperature. Okay. This is, these are all raw data associated with the time series. You could also do it for attributes of the time series. So I've linked, here's an example. This is a histogram of the change in a bunch of time series. And as I'm hovering over each point, you see these are the ones with like the really big increases. These are the ones with kind of middle increases. And then if you go to the very bottom, it would be the ones that are decreasing the most.